In this lesson, we'll talk about geometric sequences and series. A geometric sequence is a sequence with a constant ratio of any term by its preceding term. For example, 5, 10, 20, 40. If we take a term, for instance 10, and divide it by the preceding term by 5, the ratio is 2. And if we take any other pair of consecutive terms, for example 20 by 10, the ratio is 2 again. 40 by 20, the ratio is 2 as well. So we have a constant ratio of 2. Or another example, 8, 4, 2, 1, 1/2. Well, we can easily observe that the constant ratio for this particular sequence is 1/2, because 4 over 8 is 1/2, 2 over 4 is 1/2, and so on. So the main feature of a geometric sequence is the constant ratio. This constant ratio sometimes is referred to as the common ratio, similarly as the common difference for arithmetic sequences before. Okay, so we can say that generally the common ratio R is the ratio of an plus first term over the previous term, which is an. So that's the recipe how to find the common ratio for any geometric sequence. Therefore, a geometric sequence has the following form. If we mark the first term as a1, the second term is the previous term times the common ratio, right? Because if we divide a1r by a1, we get r, exactly what it's supposed to be, right? Okay, so this is the second term. How to produce the next term? Well, again, multiply the previous term by the common ratio r. So we have a1r squared, that's the third term, and the fourth term a1r cubed, and so on. Notice that the power of r turns out to be 1 lower than the index of the term. Therefore, the general an's term has a form a1 times the common ratio to the n minus first power. So we already developed the formula for the general term of any geometric sequence. Let's take a closer look at geometric sequences. Knowing that a geometric sequence an starts with 3 and has the common ratio of -3, find the first 5 terms of such sequence. Okay, so we know that the first term is 3. Let's take it. The next term is the first term times the common ratio. So it's 3 times -3. Therefore, it's -9. And the following term is the previous term times the common ratio again. So -9 times -3, oh, that's positive 27. And the next term can be obtained by multiplying 27 by -3. Therefore, we get -81. Finally, again, let's multiply this number by -3. We obtain positive 243. And so on. Notice that this sequence is an alternating sequence. The signs of terms alternate from positive to positive again, and so on. Also notice that all our terms are really powers of 3. So we could, for example, write that 9 is the same as 3 squared. 27 can be seen as 3 cubed. 81 as 3 to the 4. 243 as 3 to the 5. And obviously our first term is the same as 3 to the 1. Okay, the only thing that we still need to put in is the sign. So every second term has a negative sign. Okay, so that's how our sequence looks like. How can we find the 15th term? Well, let's write it down, a15, and we are going to follow this formula, right? a15 is a1 times r to the 15 minus 1, so it's 14. Okay, a1 is the same as 3, and r is -3 to the 14. Here we go. Negative to the even exponent is positive, and altogether we really have 3 to the 15, right? We could leave it this way because it's a pretty large number, or if we wonder how much is that, we could use a calculator. 3 to the 15 is 1434897. Very unpleasant big number, so it's probably better to keep it in a power form like this. In the next exercise, we are asked to find the general term, and here is our formula for the general term, of the following sequences. In example A, we have given the first term and r, so we just need to plug in this information to the formula, right? It's 10 times r, which is 1/2, to the exponent n minus 1. That's our general term. There is nothing else to do here. However, in the second term, in order to use this formula, we need to figure out what the common ratio r is. We know a1, that's a1, right? -2. And the common ratio r is, well, let's take the first two terms, 1 over -2. Here we go. Therefore, an equals a1, which is -2, times -1/2, that's our r, to the n minus 1. So that's our general term. Can we simplify this formula a bit? Well, maybe yes. We can combine these two negatives. Watch that the negative by 1/2 is raised to the exponent n minus 1. If we multiply these negatives by a -1 from here, then we can rewrite this expression as -1 to the n, because it's n minus 1 and another negative, so it's altogether n, right? And here we have 2 in the numerator, and denominator is 2 to the n minus 1, isn't it? So this whole thing could be actually written as -1 to the n over, after cancelling 1, 2 from the numerator and denominator, we ended up with 2 to the n minus 2, right? Because this last 2 from the denominator is cancelled. So our general term could be expressed this way. Find the 25th term of the following geometric sequences. And here we have two ways of doing so. We could either find the nth term of this geometric sequence and then find the particular 25th term, or we can directly find the 25th term from this formula. In both cases, we need to have a1, which is given here, and r. So what's our r? R is a term divided by the previous term. So 2√3 divided by 2, that's the same as √3. We can double check if the next pair gives us the same ratio. It should, because it's stated that it's geometric sequence, but just in case, let's check it. 6 divided by 2√3, when we reduce the 2, we get 3 over √3, and then by getting rid of irrationality, multiplying by √3 here and there, we ended up with √3 in the numerator, and this 3 will be gone with the 2 roots in the bottom, right? So yes, it's indeed √3. Okay, we have our common ratio. We can plug in all the information to the formula for A25, 25th term, right? A1 is 2 times r, which is √3, to the exponent 25 minus 1, so it's 24. Here we go. Now, to simplify this a bit, we can rewrite the 2, and the √3 can be recorded as 3 to the 1/2. Then it's raised to the 24. So as we see, the 2 can be reduced with 24, leaving us with the exponent 12. Therefore, a little bit simpler form of this 25th term is 2 times 3 to the 12. And we don't need to evaluate this. This is really large number, so let's stay with the factored form like this. And the next example. In order to find the 25th term, or the general term, we need to have a1 and r, right? Two unknowns. To figure it out, we really need a system of two equations. And we have two pieces of information, so yes, we can create two equations. A3 from the formula is equal to a1 times r to the 3 minus 1, so it's 2. And that equals to 0.006. The second equation can be written as a6, which is a1 times r to the 1 lower than 6, so it's 5, right? Equals 0.000006. There's 5 zeros and 6, right? So yes, we have system of two equations with two unknowns, so it shouldn't be a problem to solve it. Now, How do we solve this type of equations efficiently? Well, I would suggest to divide those equations side by side. But since this power 5 is higher than the square, then let's take the second equation as first and divide it by the top equation. Okay, so we are going to divide side by side. a1r to the 5 divided by a1r to the 2 causes that a1 will be reduced, and we end up with r cubed. 5 minus 2 is 3. Okay, equals, let's do the same on the other side. So we have 0.000006 divided by 0.006. That means that we can move the bottom decimal dot 3 places to the right, and we can do the same in the top 3 places to the right, which gives us 0.006 over 6. That's exactly 0.001, 1/1000. And the final step would be to take cubic root on both sides. That will leave us with r on the left-hand side, and cubic root of 0.001 is just 0.1. So we have our common ratio, 0.1. Now let's go back to the first equation to find a1. We will have a1 equals 0.006 divided by r square. Okay, but r is 0.1, so it's 0.1 square. Here we go. That gives us 0.006 over 0.01. Okay, if we move the decimal dot 2 places to the right, we end up with 0.6 over 1, which is just 0.6. Okay, we have all the information we need to find the 25th term. Therefore, a25 equals a1, which is 0.6, times r, which is 0.1, to the exponent 24. Here we go. We could also express this number as just 6, and instead of this decimal dot, increase the power of 0.1 here. So times 0.1 to the 25. That's the same. That really means that we need to move the decimal dot 25 places to the left to recover the number, isn't it? Okay, here's our term. How to find the partial sum Sn of the first n terms of a geometric sequence? Let's make a trick like this. First, we're going to write the whole sum of the first n terms of a geometric sequence. It is here, right? And then to annihilate some of those terms, we can multiply this original sum Sn by r and then subtract from the above sum. So we are thinking about multiplying the top row by r. That means that the first term becomes the second term, right? It becomes a1r. And write it one step to the right. So this term multiplied by r is written here. That term multiplied by r is written over there, and so on and so forth. So the last term, when we multiply by r, it becomes a1r to the n. Why this operation is useful? Well, because as we see, all these columns, except for the outside terms, cancel each other, right? When we add these equations side by side, those columns will cancel each other. That's great. We ended up with just 2 terms. So on the left we have Sn minus Rsn, and on the right hand side we have a1 minus a1r to the n. That allows us to calculate Sn on itself. How? Just by factoring Sn here, that becomes 1 minus r in the bracket, equals, we could also factor a1 over there, 1 minus rn in the bracket, and then from this equation we can solve for Sn by dividing the whole equation by this bracket, 1 minus r, right? So Sn becomes a1, 1 minus r to the n, everything over 1 minus r. Here's our formula for the first n terms of a geometric sequence. Okay, so let's display it again. Obviously, we have to make sure that this bracket 1 minus r is not 0. That means that the r is not equal to 1. When r is 1? When we actually have a constant sequence, right? But we don't need any special formula for calculating the partial sum of a constant sequence. It's enough to multiply the number of terms by the constant value of the term. So we can treat constant sequences separately. Therefore, for the use of this formula, it's okay to assume that r is different than 1. Let's take a closer look at our formula. Suppose that the absolute value of r, our common ratio, is smaller than 1. So we have some sort of fractional small number, close to 0 number, right? If we raise a number that is close to 0 to the n, when n is very, very large, this expression becomes very, very small. For example, 1/2 to 1,000, 1/2 to 1,000,000, that will be very close to 0, very tiny number. Therefore, we can state that r to the n gets closer and closer to 0 when n is very large, when n goes towards infinity. What does this mean? Well, it means that in the long run, the general term of a geometric sequence with such common ratio is actually going towards 0. So the general term is closer and closer to 0 when n goes towards infinity. This also means that we can actually calculate the infinite sum as infinity, the sum of all infinitely many terms of the sequence. This sum would exist, and it would be equal to just a1 over 1 minus r. Why? Well, intuitively, if this part is going towards 0 for very large n's, so the whole bracket is nearly 1, and we are replacing it by 1. Therefore, this whole business disappears, and we have even simpler formula, a1 over 1 minus r. So for geometric sequences with absolute value of a common ratio smaller than 1, it's even easier to calculate the overall sum of all infinitely many terms than the partial sum of the first n terms. Also, if the common ratio is actually bigger or equal than 1, then the infinite sum does not exist. Even if it's equal to 1, well, the infinite sum wouldn't exist because we would have to add infinitely many constant numbers. That's impossible. So again, in order to be able to calculate the infinite sum of a geometric sequence, we need to check if the absolute value of r is actually smaller than 1. If it's not, we will say that such sum doesn't exist. Well, let's practice. Find the S12, the sum of the first 12 terms of each geometric sequence. In example A, we have given a1 and r. So we can basically plug in this information directly to the formula, and S12 would be equal to a1, which is 5, 1 minus 2/3 to the n, which is 12, right? So notice that we are using exactly the same n for the sum. However, in the general term formula, the exponent was n minus 1. That's good to remember here, right? Everything over 1 minus r, and r again is 2/3. And here we need to just simplify, so a little bit of arithmetic. We get 5 times 1 minus 2/3 to the 12. Let's keep it as it is for now because it's pretty small, unpleasant number. We can use a calculator in the next step. And let's compute the denominator. So 1 minus 2/3 is 1/3. Dividing by 1/3 is the same as multiplying by 3. So 3 times 5 is actually 15. And then we can multiply by this expression using a calculator. That becomes approximately 0.99229. Oh, let's round it to this place value. And times 15 turns out to be approximately 14.88. I think 2 places after decimal dot are good enough. So as you see, in geometric sequences, we may end up with a rounded answer, not exact answer, because the exact answer is just too unpleasant to keep it that way, right? Okay, let's see another example. This time we have a1 because it's indicated here, it's 3. And r we need to find, right? But it's actually not difficult at all. 6 divided by 3 is 2. 12 divided by 6 is 2. Yes, that's a geometric sequence with the common ratio 2. So we are ready to find S12. S12 will be the first term, which is 3, times 1 minus r, common ratio 2, to the 12, and everything over 1 minus 2, right? Okay, so we have 3, and in the bracket, this is large number, but it's not so bad. It is an integer, right? So let's use a calculator. 1 minus 2 to the 12 turns out to be negative 4095. And in the denominator, we have negative 1. So the total sum becomes positive 12,285. Not a problem here, right? Now let's practice how to evaluate geometric sequences written in sigma notation. Recall from the previous video that anytime we have a constant under the sigma sign, we can actually pull this constant in front of the sigma, right? So that will be 5 times the sum of 3 to the I, where I changes from 1 to 5. Notice that this 3 to the I is a geometric sequence, with a1, the first term, being 3, because if I is 1, then we have 3 to the 1, so it's 3. And the common ratio, r, equal, well, 3 to the I plus 1 over 3 to the I really gives us just 3. Observe that anytime we have something to the exponent under the sigma notation, this something, this base, it's actually the same as the common ratio. So it's really easy to recognize it, right? The base is our common ratio. Okay, therefore we can go 5 times, and this is really the S5 of a geometric sequence with the first term 3 and a common ratio 3. Therefore, we can apply the formula for the first 5 terms of such sequence. It will be 5 times, and now we go a1, which is 3, 1 minus the common ratio, which is 3 again, to the n is 5, over 1 minus r, so it's 1 minus 3. And that's all. The rest is just arithmetic. So we have 5 times 3, it's 15, and then in a bracket, we get negative 242. Use a calculator to check on that one. Over negative 2. So altogether, this whole sum is positive 1815. Again, check it on your own. Let's try one more example. And this time, why don't you stop the video and try on your own first? Here we go. We can pull the constant number out of the summation, since this is the infinite sum. So we should ask ourselves a question, can we actually calculate this sum? Does it exist? Yes, it does. Just because the common ratio r is negative 1/2, so its absolute value is smaller than 1. That's why we can use the formula for the infinite sum of this geometric sequence. Okay, let's copy the 3/5 first. And then the formula for this infinite sum is a1. What's our a1? This is where I is 1, right? So a1 is negative 1/2. Keep it with the sign. Okay, a1 is negative 1/2 over 1 minus r. And r is negative 1/2 as well. So watch this double negative here. Here we go. The rest is just arithmetic. So we can multiply the negative 1/2 times 3/5. That will be negative 3/10. And then in the denominator, we have 1 plus 1/2. So it's really 3/2, right? And then change the main division into multiplication by the reciprocal. So it's times 2/3. Reduce the 3, reduce by 2. And our final answer turned out to be negative 1/5. So this whole infinite sum is pretty small. It's just negative 1/5. How come? We're adding infinitely many terms, and we ended up with just negative 1/5? Well, that's because this is alternating series. the signs of terms alternate. So while in one term we gain something, the very next term we take away something. And again, add something and subtract something. That's why there's no surprise that the overall sum is small and even negative. Finally, we have an application problem. When dropped from a certain height, a ball rebounds 2/5 of the original height. How high will the ball rebound after the fourth bounce if it was dropped from a height of 10 feet? What is the total rebound distance before the ball comes to rest? Well, let's picture out the situation first. We drop the ball from the height of 10 feet. So let's say on this diagram, the first distance, this distance, will be 10 feet. Okay? And then the ball rebounds 2/5 of it. So it rebounds up to here. This distance is 2/5 of the original distance, so 2/5 of 10. Okay, let's record this in a sequence. The first term, A1, would be the original distance 10. The second term, A2, let it be 10 times 2/5. And the following term, A3, will be whatever the previous height was times 2/5 again. So the following term would be 10 times 2/5 square, and so on. So that's our sequence. The question is, how high will the ball rebound after the fourth bounce? So this is the first bounce, second bounce, third bounce, fourth bounce. After this fourth bounce, the ball will rebound this much. Okay, so which term is that in our sequence? This is the first one, this is the second one, third one, fourth one, that's the fifth one. We really need A5. That's our question, right? So, since we already know A1, and it's easy to recognize R, the common ratio is actually how much? Yes, it is 2/5, right? It's 2/5. Therefore, A5, according to our formula, is A1, which is 10, times the 2/5 to the 5 minus 1 to the 4, isn't it? Okay, so we can evaluate this expression to be 0.256. So that means after the fourth bounce, the ball will go up by approximately 1/4 of a foot, which is about 3 inches. So 0.256 of a foot. The second question asks us, what is the total rebound distance before the ball comes to rest? The total rebound distance really means that we need to add all those rebounds theoretically forever. That means that we are actually calculating the infinite sum from I equals 1 to infinity of the above terms. How could we write this as a general statement? That will be 10 times the common ratio 2/5 to the exponent, and what should this exponent be? Well, the second term has exponent 1, so if I is 2, this exponent should be 1. Therefore, we should write I minus 1 here. If I is 1, the exponent would be 0, and that's why we obtain the first term just 10, because this part will disappear, right? Okay, first of all, we should observe that the absolute value of common ratio is indeed smaller than 1, so the infinite sum really exists, and we can use the formula A1 over 1 minus R, right? What's our A1? Well, it's 10, so it's 10 over 1 minus the common ratio, which is 2/5. See how easy we can calculate the infinite sum? That's a really powerful formula. Okay, let's calculate it. 10 over 1 minus 2/5 is 3/5. And when we flip it, we have 10 times 5/3. So altogether 50/3, which is 16 2/3 of a foot. So the total rebound distance is over 16 feet. Notice that the question didn't ask us about the total distance traveled by the ball. If that would be the question, we would have to calculate all those terms other than the first one twice, because the ball is going up and down, so it's twice for every entry except for the first one. But that's not difficult to calculate. You may want to do it as another exercise. So this is the last example that I have for you, and that's actually the last video for this course. If you bared with me till that point, congratulations! You're well prepared for the next course, for grade 12 math.